Hi everyone, and welcome to the third of 4 videos looking at some past exam questions on the topic of the equilibrium constant, Kc. As is fairly standard by now, first question comes up as write an expression for Kc. So hopefully we're getting familiar with this by now. Kc is the products over the reactants, and it's the concentrations, so we need square brackets. And remember, the concentrations are raised to the power of the number of moles in the equation. So concentration of C2H2 is to the power of 1. Concentration of H2 is going to be to the power of 3, and then the reactants on the bottom, CH4, and the concentration needs to be to the power of 2. Okay. Right, then the next question is slightly unusual. Okay, let's have a look at it. So it's saying we're investigating how to improve the synthesis, blah, blah, blah. Okay, we took some methane, we added it to a container. It's not telling us how much. We took some methane. Okay, heated it, allowed equilibrium to be reached. Okay, fine. The volume doesn't change, and it tells us how much we've got at equilibrium. And then it's saying calculate the amount in moles of H2. Then it wants us to calculate the equilibrium constant. And then the last part of this question is calculate the amount in moles of methane that we started with. So it's kind of a strange way of looking at it. I'm going to ignore the order that the question is, and I'm just going to do the ice table method that we've done before. Okay, and if we go through that method, we will end up answering all these bits of the question in a slightly different order, but it will get us to all of the answers that we need. Okay, so don't be thrown off by the fact that the question looks a bit different to how it normally does. We're still going to apply the same method. Okay, so I'm actually going to go and start answering this part first. Okay, calculate the equilibrium constant. Okay, I know when I get that type of question, I'm going to draw my ice table. Okay, so that's what we're going to do. Let's just get our reaction here. I'll write this across the top. And we're going to start making up this table again. Okay, how much did we have initially? Well, straight away we kind of have a problem because we don't know. We know we had some methane, but we don't know how much. So this could quite easily throw you off if you're not careful. Okay, that doesn't matter. As we go through the rest of it, you'll see why we don't need that. That's what they're asking us to work out eventually, isn't it? Okay, so it's not a surprise that they haven't given us that, because that's what they're going to ask us about. So we're not going to worry about that for now. We obviously don't know the changes. What do we know? We know the equilibrium mixture. Okay, so we know that at equilibrium we've got 9.36 times 10 to the minus 2 moles of our methane, and we know we've got 0.168 moles of the C2H2. Well, where do we go from here then? Because we've just got two numbers and a whole bunch of blanks. Well, the problem here is that we don't have any of the initial amounts. We definitely don't have this one. We're never going to get this one because that's what they're asking us to calculate. But we do know these two because all it said was the chemist adds methane. So they added methane, they didn't add any of these. Okay, which means we started with 0 and 0 here. Okay, remember we can always assume that initial values are 0 if they haven't told you otherwise. Okay, although it doesn't tell us the value of methane, clearly the value of methane to start with is not 0 because they added some amount of it. Okay, so this is something we don't know, but we know these two are 0. And that then allows us to work out the change here. This has gone up by 0.168. Then we can start applying the ratio. Okay, however much this has gone up by, this is going to go up by 3 times as much because it's a 1-to-3 ratio. Okay, I can't do that in my head. But 0.168 times 3, 0.504. So therefore we end up with 0.504 at equilibrium. Okay. And then we can work out the change here by applying the ratio again. Okay, however much this changed by, this should change by twice as much because it's a 2-to-1 ratio. Okay, so we want 0.168 times 2. And that is going to be a negative value, isn't it? Because we started with some and then we're going to have lost some because it's going to have turned into these things. So it's going to be minus 0.336 moles. And then we can work backwards and see how much we had to begin with. okay, by adding these two values together. Okay, so if we then add on our 9.36 times 10 to the minus 2, that will take us back to the value that we had at the start, 0.4296. Okay. Now we have our table filled in. In order to calculate Kc, we need the concentrations, don't we? So we're going to have to put an extra row in here. To get the concentration, we're going to have to divide by the volume. Where was the volume? It was 4 decimeters cubed. So we just need to divide all these values by 4 now. Okay. So 9.36 times 10 to the minus 2 divided by 4. We're going to get 0.0234. 0.168 divided by 4. 0.042. And 0.504 divided by 4. And now these are the concentrations that we can then put into our Kc expression. So Kc is going to be, get the numbers the right way round, 0.042 times 0.126 cubed over 0.0234 squared. So 0.126, no, not squared, power 3 times 0.042 divided by 0.0234 squared. And we end up with a value of 0.15. Right, so there's 3 significant figures, so 0.153. What are the units going to be? To work out the units, I'm just going to do this up here because I've got no space here. Oh, you can't see what I'm doing anyway. But if we go up here and try and work out our units, so we're going to have moles per decimeter cubed. Can you see I'm going to skip a step here? Can you see we're going to end up with moles per decimeter cubed to the power of 4 altogether on the top? Okay. Because we've got to the power of 1 to the power of 3. And we've got moles per decimeter cubed squared on the bottom. So we're going to end up with moles per decimeter cubed squared. And so that's going to turn out to be moles squared decimeters to the minus 6. So we've kind of gone through the question. We've just ignored the fact that it was in a weird order and done it as if it was in the order that we're used to and calculated Kc. Now we just need to go back and fill in the bits that we've missed. So calculate the amount in moles of H2 in the equilibrium mixture. So that was our value here, 0.504. And these are only 1 mark questions here, so it's not going to matter if we haven't shown our working out. Our working out is in here anyway, so we can use that. But because it's only a 1 mark answer, as long as we've got the right answer, the chances of us guessing this just purely by luck is very small. So that's why they're not going to be worried about the working out here. It doesn't say show your working. So, and then the other question we got was calculate the amount in moles of methane that the chemist originally added. So that was this value here, 0.4296. So we did end up working out everything that they wanted us to work out. We just didn't do it in the order that they wanted us to do. We did it in the order we wanted to do. We did it in the order that we're used to and that we're comfortable with. Yeah? Okay, final question here. This one's a little bit different. We've got a table to fill in. So it says they're repeating the experiment 3 times. In each experiment, they make 1 change, but use the same initial amount of methane. Okay. Complete the table to show the predicted effect of each change compared to the original experiment. And then read the question. Only use the words greater, smaller, or same. Okay, so we need to make sure we're using that. If you say bigger instead of greater, they are going to give you the mark, but just read it. It makes it easier for whoever's marking it, and therefore makes it more likely you're going to get the marks if you actually use the right words. Okay, so if we heat the container at constant pressure, what's going to happen to Kc? Well, that depends on whether the reaction is exothermic or endothermic forwards. So let's go back and have a look. What's it saying? Here's our reaction. Here's our enthalpy change. It's saying delta H is positive. So that means the forward reaction is endothermic. So if we heat the reaction up, the equilibrium is going to shift to cool the reaction down, and it's going to do more of the endothermic reaction. Endothermic reactions make things colder. So if it does more of the endothermic reaction, it's going to do more of the forwards reaction. We're going to shift more to the products, and so Kc is going to become greater. What's going to happen to the amount of C2H2? Well, we said we shifted to the right, so that's going to get bigger. And what's going to happen to the rate? This is nothing to do with equilibrium. Rate of reaction is a separate topic. If I've heated something up, the rate of reaction is going to increase, isn't it? Okay, if we use a smaller container, well, if you use a smaller container, what you've done is you've increased the pressure. Okay? Pressure has no effect on the value of Kc. Okay, remember, Kc is only affected by temperature. So this is one that's trying to catch you out. Kc is going to stay the same. What effect is it going to have on the amount of C2H2? Well, if we've effectively increased the pressure, the equilibrium is going to shift to decrease the pressure, and so it would shift to the side with fewer molecules of gas. So it would shift to the left, and therefore we're going to end up with less of the C2H2. So this is going to get smaller. What's going to happen to the rate of reaction if we increase the pressure? The rate of reaction is going to increase. Okay, we're going to get a higher frequency of collisions if we've squeezed it into a smaller container. Finally, what's going to happen if we use a catalyst? Catalysts don't affect the position of equilibrium at all. So it's definitely not going to affect the value of Kc. It's not going to affect the equilibrium amounts of any of the chemicals. But if we use a catalyst, it is going to increase the rate. That's going to be greater.